Good morning, everyone, and welcome to today's presentation. I am delighted to have you here. Today, we will be discussing the calibration of digital balances. The presentation is titled Dr. S.K. Singh, Ph.D., and focuses on the important process of ensuring accurate measurements with digital balances. We will cover the basic principles of calibration, the methods involved, and best practices to maintain precision. Let's get started and explore how proper calibration can enhance the reliability of your measurements. Let's talk about what calibration really means. Essentially, calibration is the documented comparison of measurement results from a balance with known reference standards. The goal here is to determine how accurate the balance is and to understand the uncertainty associated with its measurements. It's important to note that calibration doesn't automatically mean you need to adjust the balance. Adjustment is only necessary if the calibration reveals that the balance isn't within acceptable limits. Now, from a regulatory perspective, there are clear expectations. Your calibration process should comply with USP 41, balances, and related guidelines, which set the standards for proper calibration practices. Additionally, traceability is a critical concept. Your measurements should be traceable to national or international standards, like those outlined in OIML R111. This ensures consistency and reliability across different laboratories and regions. So, in summary, calibration is all about verifying and documenting the accuracy of your balance against recognized standards, ensuring compliance, and maintaining the integrity of your measurements. This foundation supports the overall theme of ensuring quality and accuracy in your analytical processes. Ensuring accurate measurement results is absolutely essential in our work. When we calibrate properly, we maintain traceability to recognized standards, which helps us verify that our measurements are reliable and consistent over time. This also plays a crucial role in minimizing measurement uncertainty, giving us confidence that our data is precise. Compliance with regulatory requirements such as ISO, USB, NABL, and OIML is vital, as it ensures our processes meet industry and legal standards. By doing so, we significantly reduce the risk of out-of-specification results, which could otherwise lead to costly errors or non-compliance issues. Ultimately, calibration is the backbone of quality assurance. It helps us deliver trustworthy results and uphold the integrity of our work. Let's take a closer look at some key guidelines that are essential for our work. First, we have USP 41, which focuses on balances. This guideline emphasizes the importance of repeatability, accuracy, and understanding measurement uncertainty. Essentially, it helps us ensure that our weighing processes are reliable and consistent. Next, there's the OIML R111 standard, which relates to reference weights. It provides classifications and tolerances, helping us determine the quality and precision of the weights we use in calibration and testing. We also need to be aware of ISO IEC 17025. This standard is all about competency, making sure our personnel are properly trained, and it also covers how we report measurement uncertainty. Accurate reporting builds trust and ensures our measurements are valid. Finally, we must adhere to GLP and GMP requirements. These guidelines govern good laboratory and manufacturing practices, especially regarding documentation and traceability. Keeping thorough records helps us verify our processes and meet regulatory expectations. All these standards and guidelines tie back to our overall goal, ensuring accuracy, reliability, and compliance in our measurement processes. They form the backbone of quality assurance in our industry. Now, let's talk about the pre-calibration preparation process. First, it's important to allow the balance to warm up for about 30 minutes. This helps ensure thermal stability, which is crucial for accurate measurements. Next, we want to stabilize the balance in a controlled environment, meaning no drafts or vibrations that could affect the reading. It's best to place the balance on a vibration-free surface and avoid any drafts or temperature fluctuations around it. Make sure the balance is properly leveled, using a spirit level, with the bubble centered. This step is essential for ensuring accurate weighing results. Before starting calibration, clean the weighing pan thoroughly. If needed, use anti-static control measures to prevent static charges that might interfere with the measurement. Lastly, always use certified calibration weights, ideally class E2 or F1 as specified by OIML standards. These steps are all about creating the ideal conditions so that your calibration process is precise and reliable, aligning with our overall goal of maintaining measurement accuracy. Now, let's take a look at the different types of calibration and how often they should be performed. First, there's internal calibration. This is built into the device itself, with a mechanism that adjusts and verifies the accuracy automatically. It's convenient because it helps maintain precision without needing external tools all the time. Next, we have external calibration. This involves using traceable standard weights to verify the accuracy of the equipment. It's more comprehensive because it checks not just accuracy, but also linearity, repeatability, and eccentricity, ensuring the device performs consistently across its range. Regarding how often calibration should be performed, a quick daily check before use is common, testing zero and small weights to confirm the device is ready. Then, a more thorough calibration, using a range of weights, should be done monthly or quarterly to ensure ongoing accuracy. After any maintenance or relocation, a full calibration becomes mandatory. This helps verify that the device remains reliable after being moved or serviced. It's also important to note that regulatory bodies tend to prefer external calibration, especially when traceability to national standards is required. This ensures the calibration process is transparent and meets compliance standards. In summary, understanding these calibration types and their frequencies is crucial for maintaining the accuracy and reliability of our measurement devices throughout their operational life. Let's start by ensuring the balance is at zero and check that it remains stable at zero. This is a crucial first step to confirm there's no drift or imbalance before we proceed. Next, we place our certified weights for calibration, and this involves multi-point external calibration. We use weights at various percentages of the capacity, specifically at 10, 20, 40, 50, 60, 80, and 100% to get a comprehensive calibration curve. As we do this, it's important to record the observed values at each point and then calculate the deviation from the expected values. After that, we perform a repeatability test by repeatedly weighing the smallest weight, say, a 10% capacity weight, 10 times. This helps us assess consistency and precision. We also perform additional checks, like eccentricity, to verify that the load is centered properly, and linearity to ensure the scale responds proportionally across its range. Now, if any of these measurements fall outside the established acceptance criteria, the next step is to either repair or adjust the equipment. Only once it meets the standards do we consider the calibration complete. This process ensures our weighing system remains accurate, reliable, and ready for precise measurements. Now, let's take a closer look at the acceptance criteria for calibration. The key point here is that the error should be within plus or minus 0.5%. If the error exceeds this range, the balance fails calibration and needs adjustment. Looking at the table, we see various standard weights, from 10 grams up to 100 grams, along with their observed weights, calculated errors, and percentage errors. For example, when we test the 10-gram standard, the observed value is 10.002 grams, which results in an error of 0.002 grams and a percentage error of just 0.02%, well within our acceptable range. Similarly, for the 20-gram weight, the observed value is 20.02 grams, with an error of 0.02 grams, translating to 0.1%. Again, this is within the plus or minus 0.5% limit. As we move to larger weights, like 40 grams, the observed value is 39.98 grams, with an error of minus 0.02 grams, or minus 0.05%. Even at 50 grams, the error is negligible, just minus 0.002 grams or 0% error. Looking at the 60-gram weight, the observed value is 60.03 grams, with a 0.03 gram error, which is only 0.05%, still comfortably within our criteria. The 80 gram weight shows a minus 0.03 gram error, or minus 0.04%, and the 100 gram weight has an observed value of 100.05 grams, with a 0.05 gram error, or 0.05%. All these measurements confirm that as long as the errors stay within plus or minus 0.5%, our balance is properly calibrated. If errors go beyond that, it indicates a calibration failure, and the balance needs to be recalibrated or checked. This log of calibration ensures accuracy and consistency in our measurements, which is essential for maintaining quality standards in our work. Let's talk about repeatability, which is covered by USB 41. The key idea here is that the variability in your measurements should be very small. Specifically, the criterion is that 2 times the standard deviation divided by the nominal value should be less than or equal to 0.1%. For example, if you perform 10 measurements and your standard deviation is 0.0001 grams at a 10 gram weight, then doubling that SD gives you 0.0002 grams. When you express that as a percentage of the nominal weight, you divide 0.0002 by 10 grams, then multiply by 100, which results in just 0.002%. That's well within the acceptable range. Now, moving on to accuracy. Accuracy is about how close your observed measurement is to the true or nominal value. The error is simply the observed value minus the nominal value, and the percent error adjusts that error relative to the nominal to give a clearer picture. For instance, if your nominal weight is 50 grams and you measure 49.998 grams, the error is 0.002 grams. When you convert that to a percentage, it's about 0.004%. This helps us understand how accurate our measurements are. Finally, measurement uncertainty gives us an idea of the potential variability in our measurements. It's calculated as the standard deviation times 2, divided by the true value. So, if your SD is 0.02 grams at a 50 gram weight, the uncertainty would be 0.02 times 2, divided by 50, which equals 0.0008, or 0.08%. In summary, when we're calculating accuracy, uncertainty, and repeatability, these concepts work together to give us a comprehensive view of our measurement quality and reliability, which is essential for ensuring the precision and accuracy required in our work. Let's start with the concept of minimum weight and uncertainty. The minimum weight, often calculated using the USP formula, is essentially the smallest amount of material we can weigh accurately considering the variability in our measurements. The formula is minimum weight equals twice the standard deviation divided by the maximum allowable uncertainty, or Umax. Typically, Umax is set at 0.1%, which helps ensure our measurements are within acceptable limits. For example, if our standard deviation, SD, is 0.0001 grams, and our Umax is 0.001, then the minimum weight would be calculated as 2 times 0.0001 divided by 0.001, which equals 0.2 grams. This gives us a clear threshold to work with for weighing accuracy. Now, regarding uncertainty reporting, it's become a required practice according to USB guidelines and ISO IEC 17025 standards. Properly reporting the uncertainty associated with our measurements is crucial for transparency and compliance. Moving on to performance checks, these are essential to maintain confidence in our measurements. Repeatability involves taking multiple measurements of the same weight and calculating the standard deviation to see how consistent our results are. Linearity tests involve measuring across the range of weights we expect to use, ensuring our scale performs accurately at all points. Eccentricity checks involve placing the weight at different zones on the pan to verify that the readings remain consistent regardless of placement. Lastly, drift testing means taking multiple readings over time to detect any gradual changes in the scale's performance. All these checks help us confirm that our weighing process remains precise and reliable, aligning with the overall goal of ensuring quality and compliance in our measurements. Let's take a look at the typical schedule for calibration to ensure our equipment stays accurate and reliable. First, it's important to perform a quick daily check before each use. This simple step helps catch any obvious issues before the equipment is put into operation. Next, a full calibration should be done monthly or in accordance with the SOP, Standard Operating Procedure. This regular calibration ensures the device maintains its precision over time. There are also specific situations that require calibration outside of the regular schedule. For example, after relocating the equipment or following maintenance, or if there's been a power failure. These events can affect the calibration, so a check is essential to confirm everything is still accurate. Similarly, after repairs or if you detect any major drift in measurements, recalibration is necessary. This helps us verify that the equipment is functioning correctly and providing trustworthy results. Overall, the calibration frequency is designed to balance operational efficiency with the need for accuracy, ensuring the integrity of our measurements at all times. Now, let's talk about the key items to record during calibration. First, we need to note the balance ID, including the model and serial number, to ensure traceability. Then, record the calibration date and time, along with the operator's name, so we know exactly who performed the calibration and when. It's also important to document the standard weights used, their IDs, and their traceability to verify the calibration's accuracy. Next, we record the observed values, any deviations from expected results, and the percentage error, which helps us assess the performance of the balance. Finally, we document whether the balance passed or failed the calibration, along with any corrective actions taken if issues were found. Moving on to documentation and compliance, what exactly do we need to keep track of? First, calibration certificates for the standards used are essential. They serve as proof of the weight's validity. We also need to maintain calibration logs that include weights, readings, and percentage errors, providing a detailed history of calibrations. Uncertainty and precision results are critical to understand the reliability of measurements. If any outliers are identified, documented corrective actions are necessary to address those discrepancies. And of course, we must keep track of the next due date for calibration to ensure ongoing compliance and accuracy. This thorough documentation not only supports quality assurance, but also helps us meet regulatory requirements and maintain confidence in our measurements. Now, let's talk about some best practices to ensure our calibration processes are reliable and compliant. First, always use certified calibration weights that are traceable to recognized national standards. This is crucial because it guarantees the accuracy and consistency of your measurements. Combining internal calibration with periodic external calibration creates a more robust control system. Internal checks help us maintain daily accuracy, while external calibration confirms our standards remain solid over time. It's also essential to ensure our operators are properly trained. Regular training keeps everyone up to date with the latest procedures and regulatory requirements. Speaking of procedures, our standard operating procedures, or SOPs, should always be current and include version control. This way, we can easily track changes and ensure everyone follows the latest guidelines. Additionally, having a quality assurance review and approval process helps maintain high standards. Traceability to national and international standards is non-negotiable. It provides confidence that our calibration results are valid and comparable globally. Finally, scheduling the next calibration according to the SOP ensures we stay proactive and consistent in our calibration cycle. By following these good practices, we reinforce the integrity of our calibration program and uphold the quality standards that are fundamental to our work. For further support, please don't hesitate to get in touch. We're here to help you with any questions or additional information you might need. Feel free to reach out through the contact details provided. Thank you so much for your time and attention today. I truly appreciate your interest and engagement. Remember, we're committed to supporting you every step of the way. Thank you again, and have a great day.